He said he's coming back on Wednesday. We're going to finish up talking about this idea of member releases. Before we did that, I went, because I love this shit, right? We talked about this idea of shear connections, right? You guys are all familiar with the SEAL manual, right? This is the one I learned on. It's got a few miles on it, okay? Right, in part 10, it talks about simple shear connections, right? If we first go to 10.4, which is the very beginning of it, when it talks about force transfer. The ends of members with simple shear connections are normally assumed to be free to rotate under load, while simple shear connections do actually possess some rotational restraint. This small amount can be neglected, and the connection idealized is completely flexible. What they tell you, though, is that you have to go and make sure that it meets this AISC specification section J1.2, which talks about connections. We got here, J1.2. Talks about simple connections and says, hey, you've got to do this, right? And this is the law. This is chapter J. This is in the specification, right? Part 10 is just a helper, right? All of the front end of this book is just to help you design things. Chapter J is in the specification, AISC 360, and this is the code or law, right? And so as we mentioned, right, so they're also accepting the fact that there's going to be some resistance in that connection, but we're going to assume that it's flexible. The way they allow us to do that is if we go to the shear connections tab here, right, under a conventional configuration for a single plate connection, right? They talk about what's going on with the hole type. Is it short slotted holes, standard holes, right? The number of bolts that are acting there, well, as you can imagine, as we move up with respect to the number of bolts, well, now we end up with this long string of members, right, or connections, connecting elements, bolts, that give us more and more torsional resistance, right? So when we get down here and we're using standard holes and we have 6 bolts or more, the eccentricity we use is the actual eccentricity of the bolted connection. Whereas if we have less than that, we can use half that eccentricity, A, which is the distance from the face of our support to the center line of our first bolted connection row, right? And this is for just single rows of bolts. When we go to double rows of bolts, because we design a DCI, you jump into this extended configuration with a lot more checks. These are the design checks that are required for a simple shear tab in the conventional configuration, which is really nice, right? The one thing that I was mentioning in class here, right? We were talking to Aaron, he's not here to listen, right? But they give us requirements on what's the maximum thickness of our plate or the web of the beam. And the idea here is to not make this too stiff so that there is the ability to almost plow into the edges of our bolt holes, whether it's in the steel plate or in the web of the beam, in order to get some additional flexural, flexibility in the connection, okay? And so that's where, if you calculated it for a 7/8 inch diameter bolt, right, the thickness of our plate, right, is like 1/2 inch or something like that for most of our configurations. And for typical shear tabs, what's the thickness? Come on, you guys are dealing with it
We don't have
in the
it.
connections. Have you seen the details? What shear tab thickness do you usually use? If you could guess, if I'm saying the limit is 1/2 inch, what do you think the shear tab that everyone uses?
1/4 inch?
What?
1/4 inch?
In between, 3/8.
I was gonna say 3/8.
3/8 plate is typically what the shear tab dimensions are. Okay. So isn't that cool shit? It's right there. So then that's why when we do VA, we can then do, right, simple connections. We release the forces that are acting. And when we do that, then VA has to go through this whole method where it partitions the matrix, essentially separating out, right, moving. We're going to have indices, right? Our original stiffness matrix is going to be, right, a vector of forces that create zero displacement. So this column is all about U1, second column V1, U2, V2, and so on, right, and rotations. And so what we end up doing is we rearrange this stiffness matrix to rearrange it for, okay, now we have fixed or non-release degrees of freedom columns and rows associated with each other. All the released degrees of freedom are gonna be down here. And then you have these columns and rows that relate both fixed and released degrees of freedom. So we go through this method of partitioning, separating this stiffness matrix out. You multiply it out, you solve one equation for the other, dr is what you solve for. And we plug it all back in, and we end up with this equivalent stiffness matrix, right? And that gives us some values in this 6x6 matrix that then we can plug back in. The last step here is to assemble into what we would call the corrected K matrix. It'll be a matrice where our rows and columns associated with the released degrees of freedom are 0. And the rest are from our equivalent stiffness matrix that we calculated, right? Right, because we can't have a stiffness because we can't have a force, right? We need to have a displacement though, right? So our D matrix has values. We can have a rotation, right? We can have a translation, but it doesn't translate to forces because we're saying that we can't have forces there, right? We can't have moments, we can't have forces at our nodes. So what happens, right? How can we have this get messed up? Well, if the element is over-released, handwriting is prime today. All right, so we've got a beam element, and we released it such that it could translate and rotate at the end of it, right? And we have a simple support at the other end, right? Where we can have no translation, but it can rotate. This is over-released, right? That isn't a stable condition. So what ends up happening is our KRR vector, or this portion of our stiffness matrix when we partition, right? These values right here are going to be singular, and because that's singular, right, we can't find our K equivalent, or we can't invert it.
What does it being singular actually mean?
It has to do with when you take the determinant. The determinant is
Like
zero.
0 by 0.
Because you can't take the inverse or something?
Yeah, because when you take the determinant, it's 0, and when you're taking the inverse of a matrix, you're dividing by the determinant.
Yeah.
So you can't divide by 0. Singular. So that means that our K equivalent can't be found, right? Because we can't take the inverse of it. So as I mentioned, right, if we looked at, get this here, if we looked at a column in VA, and we had two nodes, right, top and bottom, and we pinned the base, right, and we pinned the top, right. In VA, this would be unstable, right? It could not analyze this. And it is what?
Oh, rotating.
Spin.
Yeah, this thing can spin in this direction, right? We're not actually fixing it from rotating about its own axis.
If you're working in the 3D view, right, but like if you were in that 2D planar view, then that would.
Yes. Yes. I would recommend always going in the 3D view. I would, but you don't have to, they give you that option. I think, did they still give you that option?
Yeah, I feel like a lot of the preliminary stuff we've done in VA has been all.
It's all
In the,
2D.
in the plane frame, not space frame.
Yeah, exactly.
Yeah. Cause there was a time when they had it and then they took it away and said, no, we're not gonna allow you to do 2D, and then they must have put it back in, which I think you're right, yeah, in 19. Okay. So that's kind of what I wanted to capture when we were talking about some of the beam element, oh, wrong one. Intricacies as it relates to implementation of, practical things that we're doing as modeling when we model structural, right, systems. Right, so we now have essentially looked at a beam element that VA uses, right? When you model something in VA, a little bit different in the sense that VA has the degrees of freedom in the 3 dimensions, right? We were just looking at the 2 dimensions, right? There's gonna be a Z1 and a Z2, right? UV and Z, okay? And then we'd also be able to load it in that Z direction also, right? Put a uniform load and say weak axis bending of a beam, okay? Elasticity elements, okay? Started, you guys got to do this the first homework of this class, right? We went through and did the column that was made out of concrete, right? And to look at whether or not our uniaxial assumption was correct, okay? Well, you used an elasticity element to model that, okay, in VA. In VA, they use the Ullmann triangle, which we'll talk about in a little bit. And we're gonna start by looking at the constant strain triangle, which I'm sure some of you in Ladine's class have already gone over, okay? Right? But the Ullmann triangle is just a slight variation of the constant strain triangle. So VA is essentially using a constant strain triangle, right? So finite element programs, right, have what we would call a membrane element, right? That can be used in plane stress applications, right? A lot of things we have are shear walls, right? That's a very in-plane driven membrane type element. Not a lot of stress happening out of plane. Okay, gusset plates are another one that's important. Bending models for, say, we could look at diaphragms and tanks and things like that. Okay, a lot of times we can just use a membrane element. The reason why VA adjusts with respect to this Ullmann triangle, and then they also include another element when you have it look at bending, which we'll talk about in a little bit, because in a membrane, right, the thickness, it influences our stiffness, but it's not actually modeled, right? So it's going to affect the stiffness based on contributing to areas, right, the thickness of our plate, but not necessarily going to affect the actual stiffness because we're not using it as a bending portion, right? It's more affecting the area over which the stress is acting, okay? One thing that becomes very important with these elements is mesh refinement in order to ensure proper convergence, okay? Because as you can imagine, well, especially when you start talking about constant strain triangle, hence the name constant strain, right? So we must have a linear displacement function. If we have a linear displacement function, right, we take the first derivative of that, it's gonna be a constant, okay? The configuration of these, if we have constant strain, in reality, we don't have constant strain, right? And so based on the sizes and complexity of our plate elements that we develop, right, we can essentially make this constant strain jump across things that we don't necessarily want them to, right, for like great distances. And so we want to make sure that our refinement is pretty tight, because if you looked at a shaded like we did in our concrete column models, right, and with our by hand calculations we did at the very beginning of the class, we had this constant strain, right, this jump. And as we noticed, right, that our convergence was very important with respect to how those stresses and strains jumped from one element to the next. So in order to better fit our line of the exact solution that we derived, we'd have to really break up that column element, right? So that plays a huge role in plate elements to make sure that we have the proper refinement at the locations we have, right? And more importantly, having the proper refinement at the locations where we are looking at results that we want, right? We're trying to pull things out of it, right? So a constant strain triangle looks something like this, right? This is a 3-node, and we'll talk about in VA, I don't know if you guys have noticed, you can draw a 3-noded plate or a 4-noded plate. And if you draw a 4-noded plate, what they're really doing is creating 4 triangles from that 4-noded plate. It's called condensation. And they develop 4 triangles out of, right, a rectangle, okay? And there's reasons for this, we'll talk about that when we get to that. But for this case, we're going to talk about the triangle. So we have 3 nodes. We have 2 degrees of freedom at each node, right? It can translate U1, V1, right? U2, V2, U3, V3. It can have an area, right? A thickness. It's going to have a modulus of elasticity, and it's going to have a Poisson's ratio, right? I'm not talking about slender elements anymore, right? Poisson's ratio, the relationship to strain, right? Or stress acting in 2 dimensions, right? So as we took a column and you squished on it, right? It's going to displace outward, conservation of mass sort of thing. So it's gonna have all these material properties associated with it. It's gonna have this Bx and By, we're gonna call these body forces. Can you hear that buzzing sound over here, James? Or is it just me?
No.
Okay. Body forces in the X and Y direction. Body forces are kind of volumetric forces. Self-weight would be a good example of a body force. Right? Tractions. We're going to have this traction force in the Y direction. Traction. X direction, traction. Right. These could be forces along the length, they could be forces along the side, right? We could have a example would be if you modeled a diaphragm in a building, right? And you had wind loading on the walls and you didn't want to model the walls, you just wanted to model the diaphragm or the lateral system thereafter. You could then put a line load on the edges of our diaphragm, right? That would be a traction force that would be acting on the boundary of our plate, right? Our constant strain triangle, okay? You could do a line load, right? Associated with, say, a shear wall landing on a diaphragm, and you're imposing that line load into the diaphragm, right? Instead of having, say, a uniform load acting like this on this side, you might have a line load that's acting along the length of, between 2 nodes. So as I mentioned, the element has 6 degrees of freedom, U1, V1, U2, V2, U3, V3. How many generalized degrees of freedom? 6. So we have 6 generalized degrees of freedom, but we have 2 displacement assumptions, right? In the beam model, we had a displacement assumption, and then we had a rotation, right? We have displacement and rotations for our degrees of freedom. Well, because there's a relationship between displacement and rotation, this was the derivative. In this case, we don't have that luxury, right? So we have 6 degrees of freedom, so we have 6 generalized degrees of freedom, so 6 factors that we can use to develop displacement functions. So we really only have 3 for each of these, right? So when I say we will use a linear displacement assumption, that's the only option we have, right? I mean, we could do powers as a greater, right? We could go A1 plus A2x plus A3y, right? That would be a linear assumption. If we really wanted to, I could do x squared, y squared. But as we talked about Pascal's triangle, we want to always capture our lower order terms first. It helps with respect to convergence and contributions, right, of our displacements. So we don't want to go squared. We're going to use a linear. If we wanted good performance, we want to use lower order terms first. We want to make sure we capture the contribution in both directions, spatial coordinates, x and y. We got that, and we got our constant, so that worked out nicely, right? A4 plus A5x plus A6y, right? So those are going to be our assumed displacement functions for the displacement in the u direction and v direction as it relates to our coordinates x and y. If we pull this back and look at, combine these into matrix notations, we're going to get something that looks like that. Assume Aaron's not coming today, Elias. It's a good assumption, huh?
Yeah, that's right.
Cool.
Probably had to get gas and then you realized how expensive it was and then couldn't get
And
gas.
just, yeah. Started panhandling out there trying to get someone to buy him gas.
Yeah. Just had to go home.
He makes good money at Hicks, he has to.
I know, I'm just joking. That'll
Gotta
be
be.
even more this weekend.
So now, as we know, we're really heading for shape functions, right? So in order to get shape functions, we create this matrix A, which is our displacement function evaluated at our nodes. So really this becomes 1, x1, y1, 1, x2, y2, 1, x3, y3. Similarly, we would look at our nodal degrees of freedom, V1, V2, and V3. We invert, right, to figure out what our generalized degrees of freedom are. Where if we invert A, we get this big old mess of shit, right? 1 over 2A, A being the planned area of the element. Can we compromise? Can we go like a little bit? Man, I'm just roasting, okay? Sorry. I'll just say something if you want me to close it, but just give me at least a minute here. All right? So we've got our A matrix, right? Invert it. We invert it because in the end we're going to want to take it times our X matrix, right? Which was our matrix. That is our displacements. So we put it all together. Right, we usually want our matrix to incorporate both our degrees of freedom in the u direction and the v direction, or x and y. So we get a negative 1, 0, 0, which is just essentially smashing all of our degrees of freedom together. Now, as I mentioned, right, our displacement functions as it relates to our shape functions, right? It's going to be n times d. Well, we have our d matrix C off to the right there. Our n matrix C, as we know, is just x times the inverse of A. In this case, it was 1 x, y, 0, 0, 0. 1 x, y. Then we had A inverse, oops, squiggly. 0, squiggly, where x inverse of A we know, and we've done this many times now, that's our shape function. Man, we're cruising today, this is sick. I don't know if you guys are just tired because of the weekend. Aaron's not here, we have a lot of disruptions, okay? This is good. All right. So now our N matrices, as normal, we get this contribution from each of our degrees of freedom. This is U1, U2, and U3. Gonna look something like this, right? Because we have our A inverse.
Would that be like 4, 5, 6, or just 1, 2, 3 again?
Oh shit. Yeah, no, 1, 2, 3. Because it's U1, V1. Or sorry, U1, 2, and 3, V1, 2, and 3. Right? Normally, though, we group our displacements based on nodes. Okay? Nodes 1, 2, and 3. So we're going to do U1, V1, not U1, U2, U3. So that just means we're going to rearrange this. U1, V1, U2, V2, U3, V3. If we do that, now this becomes N1, 0, N2, 0, N3, 0. Where N1, N2, and N3 equal this mess of shit, okay? Gets pretty complicated, I can't just write it out very easily. So it ends up being this term P plus y23x plus x32y over 2a. Well, what does that mean? Well, the cipher here is this is P I, this is y, I, j, and this is x, I, j. So what does that mean? Well, when I say N1 is P23, that means it's x2 times y3 minus x3 times y2. Right? So those are the coordinates of our nodes, right, for node 1, 2, and 3. And same with yij is the y at, say, node, so if it was 1, 2, it would be the y at 1 minus the y at 2. Similarly for x, right? And the reason why these are denoted as N1, N2, and N3, right, is these are the same too, right? Because our displacement assumption was linear with respect to our u dimension and our v dimension, our shape functions are going to be the same, right? We really have 3 shape functions that give us the nodal degrees of freedom in the u direction and the v direction, right? So for u1 and v1, you would multiply the nodal degree of freedom of u1 and v1 at node 1 times n1, right? So it'd be n1 u1 plus, or not plus, but then you would do n1 v1, right? The shape functions become the same, and that's why we don't have 6 of them. Because our displacement assumption was both the same, it's essentially the same, right? Linear. Elias, do you believe me?
I believe you.
Okay. Just not argumentative today. Just none of you are. It's just weird.
Just
What the fuck?
accepting it, I don't,
You guys are accepting it.
don't know what's going on.
Scaring me.
Still trying to absorb what's happening.
Yeah, like,
Okay, maybe I should
see
move
that-
faster. This is the key. I just move really fast.
I see this
And-
stuff, but I don't know how to apply it necessarily. It's just like, yep, these are.
We'll apply it
equations
soon
that
enough. We're
work.
gonna give you a homework this week.
What?
This week?
Yeah, why can't I give you a homework this week?
Better be short.
The other one's due when? Today? Is it today?
Wednesday.
Wednesday? Yeah.
You're
Most of you got it done before the end of last week.
So? It's almost
So-
spring break.
so-
What happened spring break?
Man, see, here's the arguments. Here we go. Bring it on. Now I'm ready.
Assign homeworks?
Now I'm ready. Oh man, I'm an asshole. God, what a dick. Well, as we've done with all of our elements, right, we're doing energy. Okay? And in order to do energy, we need this strain displacement matrix B, right? Because we need to find the strain energy that's happening, which we know the strain energy is a function of the strains, right? And we need to relate those strains back to nodal degrees of freedom, and we do that through this B matrix, right? The strain displacement matrix. And so if we write out normal strain, epsilon xx, right? Normal strain in the x and y, this would be normal strain. Okay. And then we have shear strain, right? Epsilon xy, or a lot of times denoted as gamma xy. This is shear. Well, we all know it, strain is the change in length of the original length. So if we relate it back to normal strain, it'd be the partial of u with respect to the partial of x, right? Partial of v with respect to y. And our shear strain, if you remember, we've got shear strain is, if we had a square block, look like this. We had some dx, partial of x, I guess, partial of y. Some small distances, x and y, right? It's going to be the change in our u with respect to y plus the change in v with respect to x. Right? It's essentially the distortion of a square element. So it's how does our u displacement, right? How far does this move over? How does it change in u direction with respect to moving vertically? Plus it's the change in y direction with respect to moving horizontal, right? So that's the distortion. And this would be delta u. This would be delta v. Right? How is that line moving up? How is the vertical line moving over? We're going to add those together. That gives you the overall distortion of our element. And that gives us our strain. Well, if we put this in matrix forms as it relates to our displacements in the x and y, or u and v, we get something like that, right? And if we relate it back to our, oops. Nodal degrees of freedom. We know UV, that displacements are really the shape functions times the nodal degrees of freedom, right? Or nodal displacements. We multiply that, will give us our strains. And we know that this strain displacement matrix is our relationship of our nodal degrees of freedom to our strains. So it's really just our derivative or our partial matrices times our shape functions. Well,
Other matrices have any names?
do what?
The top, like, three there, those matrices, do they have like a,
I mean, that's all we're doing is, this is strain, right?
yeah? Guess they probably always do like A, B, and,
No.
okay,
No, I'm not gonna do it this time.
just didn't know. Just was curious, just
No,
like
This
putting
is
it in
strain,
that one.
this turns into strain. Once we pull the displacements out in the u and v directions, then this becomes, right, a derivative of our displacements, or our partials of our displacements, and then we just rearrange our displacements for our ND, right? Shape functions times the nodal degrees of freedom gives us u and v. Multiply that by our partials, and we end up getting our strain displacement. Well, if you multiply, right, this matrice times our shape functions here, right? That upper matrice, we end up with this 3/6. Which is B, oops, sorry, this is B. And as you can see here, these are all constants, right? Because we have a linear displacement assumption, right? We had linear shape functions. They related to x and y. Well, you take the derivative of those with respect to x and y, and you end up with a constant, right? They're only to the first degree. And so we end up with our strain displacement matrix. Okay, I'll let you guys have your heat.
Just about to say that.
See?
A little chilly.
Saved you. Saved you. All right.
And that is the area of the element again?
Yes, that's the
Is
planned
that
area of
something
the
that we
element.
define in terms of x and y, or would that?
It would be, it is defined in terms of x and y, right? But it's based on your nodal coordinates.
Okay.
It's based on your nodal coordinates. Right? Well, as we know, right, we need to know strain, but we need a constitutive relationship. That's the thing that relates our strain to our stresses. If we use Hooke's law, okay, and we look at plane stress, right? We could essentially look at two different models for a plate. We could say plane stress or plane strain. Any ideas why we would want to look at plane stress over plane strain for a plate? Looking at what becomes zero, right? With plane stress, our normal stress in the z direction and the strain and the shear stress, right? These are just shear stress xz and zy are also zero. Versus if we assume plane strain, that assumes that the strain in the z direction is zero. And same with our shear strains on the z face are also zero. Modeling a plate, okay? Modeling a plate, it is why we might look at plane stress. What configuration would we look at plane stress for? What would be let's see, let me think.
You're saying
Would we do
principal
mechanics?
stresses.
Well, when we look at mechanics, right, a lot of times most of the time we're assuming plane stress, right? There's a reason why we assume plane stress. Because something about the plate is in such a way that our stresses in the z direction are at least very, very small, or they're close to zero. Right? What's one thing that we decided we weren't going to model, but we were going to give it a parameter?
The thickness.
The thickness.
Just some
So which
small
one would we use, like with respect to thickness, would we use plane stress for a really thick plate or a really thin plate? Really thin, yep. Yep. Same with a lot of the members that we deal with in structural engineering, right? Wide flanges, tubes, all those things, they have very small thickness. So we assume that the stresses seen through the thickness of our element are near zero or zero, right? Plane strain are for very, very thick plates, right? Where you would assume that even though it has stress, it strains such a small amount because it is super, super thick that we can assume the strain in that plate is zero. So we could say this is for thick plates. This is for thin plates.
Is there a parameter for thin versus thick? Roughly, what qualifies?
I mean, I'd say generally speaking for structural elements, you would be in the thin plates, right? Versus if you were looking at, say, a really, really thick mat foundation, right? That might be like 4 feet thick, right? Then you're gonna start looking at some of the plane strain potential where you're gonna have very little strain in the z direction, but you're going to have stresses. Well, we have two different, right, Hooke's law, if you will, or constitutive relationships. If we start assuming that the strain in the z direction is zero, or on the z face is zero, right? That's both normal strain and shear strain. And then on the plane stress side, if we assume stresses on normal to the z face are zero. Well, if we're on the plane stress side, we get this E, right, modulus of elasticity, 1 minus Poisson's ratio squared. Poisson's ratio Oops. Plane strain, we get this relationship. Gets a little more complicated as it relates to Poisson's ratio. Oops, can't even read that. So before, right, we had our strain energy equation is the area underneath the stress strain curve. And we had this 1/2 times an integral over the volume of stress times strain over times dV, right? Or over the volume. Well, that stress we determined was the strain times E. Well, now instead of just having E, we're gonna have this constitutive relationship, right? Which relates E to strains that gives us stresses. It's a little bit more involved, right? We start looking at the fact that Poisson's ratio is going to affect what's going on in one direction versus another direction in this plate.
Is that like the stiffness matrix?
This is our constitutive relationship that relates our strain to our stress, right? It's just the same as Hooke's law where we had E epsilon is stress, right, is sigma. Well, now in the plates, we've got more going on in the X and Y direction, so we have this kind of coupling of our strains, right, or our stresses in our two directions with respect to the displacements that are happening, right, in our two directions. It's no longer a 1D relationship. We now have a relationship that's 2D.
So
So
are
it's,
you gonna have to like pick one of these to use, or they just get kind of incorporated into one thing?
yeah, I mean, when we,
Like
you're
when
gonna,
we start to
we're,
do something, we're gonna be like,
yeah,
we
when
use
you,
plane stress, or are we gonna use plane strain, or
Yes.
is it all, okay?
no. Yep. Which it'll be, I mean, 90% of the time we're in plane stress.
That's the thing you change manually when you're modeling, or does it have parameters?
Yeah.
that kind of-
So
That's
what's,
kinda what I mean.
yeah, oh,
How
I
do
see what
you-
you're saying.
Like,
I
what's-
see what you're saying.
know what's
So in VA, in the almond triangle, they actually consider three-dimensional, like they actually look at the stresses on that other face. And so in that case, right, we don't have this assumption of plane stress and plane strain anymore.
So they
This
say
is
you like
looking
a
at,
step
this is
further.
looking at a membrane element, so you start ignoring what's going on in the out-of-plane direction. Which in VA, when you model a plate, it can do both. So it's really looking at the membrane stresses, but then it tacks onto that, the out-of-plane stresses and forces that are going on. And when you're in VA, and when we talk about modeling like diaphragms and stuff, there's a little button you can click that says ignore bending. And then will start taking out that third dimension. The fact that they're no longer going to take into account the thickness as it relates to stiffness. Okay. So it's just trying to simplify it and just start
Okay.
looking at a membrane
But like
element
VA is
first.
kind of on another level where
Yes.
it does consider these things
Yes.
and doesn't make that assumption. Okay.
Yes. Yeah, when you choose a material in VA, it has a Poisson ratio attached to
Yeah.
it.
Okay.
And we'll walk through that. I think what we'll end up doing, just for light of time, I printed off a couple papers that go through the derivation of the elements with which VA uses with respect to both a thick material and a membrane material. And for a membrane, it used the almond triangle, and it adds another couple degrees of freedom, which we'll talk about when we go through it. And then it also goes through another derivation of a different element that was derived based on somebody else's publication that then starts considering what's going on with respect to rotations and displacements in the z-axis, which becomes important in structural engineering when you start looking at thick things like footings are a good example of that. Right? they're kind of deep beams, if you will, if you guys were in concrete, right? Span to depth ratio of 4, less than 4. So we now have this constitutive relationship. We're going to again use the principle of stationary total potential energy. We're going to calculate what our strain energy is. We're going to calculate what our external work is on our system. And from previous, right, we got all of this, right? It's the area under the stress strain curve. We have stresses times our strains over the volume, 1/2 of that, okay? In this case, we substitute in, we know that the stress transpose is D transpose times B transpose times E. Now we're going to have a matrix C associated with E. It's no longer, right, just a single constant value. And it still is constant, right? It doesn't waver with respect to X and Y, right? You could multiply that out. You know the material, you know what E is, you know Poisson's ratio. All of these become constants. It's just the fact that there's a coupling going on between displacements in the X direction and the Y direction. So we go through some matrix math and we end up with this equation. We pull out our nodal degrees of freedom, right, on either side of our integral because they're not a function of X or Y, right? There's no degrees of freedom. So then we have our stiffness matrix that we develop. Same with when we develop, well, so then this boils down to just 1/2, right? D transpose K D. Work, we know, is force times distance. So if we have our nodal forces, we just simply multiply those by our nodal degrees of freedom, right, or distances over which those forces act. Then we have these traction forces. Well, traction forces act over the area. So we're going to have now the displacement, our nodal degrees of freedom, times our traction forces. That'll give us what the energy is associated with, or the work that those traction forces exert. Take that integral over the area. Same with body forces, right? This would be like self-weight is the best example I could think of, right? That would be over the volume of what's going on with respect to the weight of this element. So we have really our work of nodal plus surface plus body, right? Which if we pull out our nodal degrees of freedom, we end up with this equation for the area plus the integral over the volume, shape function times the body force in the X, body force in the Y over the volume, right? Essentially substituting in our displacements over which our surface forces and our body forces act are really the nodal displacements times our shape functions, right? Same thing. We can make that substitution. Damn. All right, well, we'll stop there, I guess. All right, I expect a little more conversation next time we meet, all right? A little more disruptions,
You like it now?
a little more questions. Yes.
We could ask you where the shape functions are derived, but we're just gonna call that as it is.
The shape functions are derived. It's x times the inverse of a.
Yeah. We didn't do all that. We're just gonna take them as that's what it is.
That's what they are. If you were to run through that calculation, that's what they are. You could put it in MATLAB with a linear displacement assumption, right? Take that times the matrix C over which you evaluate all the nodal points with respect to those displacement functions, and you would end up with those equations.